Hello, we are Team H210. My name is Rohant.
I'm Ryan.
And I'm Rithik.
Purdue faces a pressing problem when it comes to ensuring the safety of pedestrians and bikers alike. This project is important because it fosters a safer environment for travelers inside of the campus. The client is the College of Engineering's Faculty Affairs Committee, and the stakeholders are pedestrians, skateboarders, vehicle drivers, students, and staff. The criteria and constraints of this project is that the solution must be desirable, must be effective, it must be economically viable, and it must be technically feasible.
We had 3 alternate designs. Our first one was called the Cyclist Assist System, and this consisted of an ultrasonic sensor attached to a mirror. When an object in the blind spot is detected, a noise will be made from a sound buzzer which will alert the cyclist that someone is in their blind spot. Our second design is the Intersection Attention Boost System. This again consists of an ultrasonic sensor which will detect movement of cars across the street. When a car is coming into the intersection, the ultrasonic sensor will detect it, which will then trigger a noise and light system to alert pedestrians. So if they're listening to music or on their phone, they'll be notified that a car is crossing the street and they'll hopefully not cross. Design 3 is the Obstructed View Assist System, and again this encompasses an ultrasonic sensor and a sound buzzer. In areas of low visibility or obstructed viewpoints for pedestrians, the Obstructed View Assist System will notify them when a bike is coming through they would potentially not see. For our alternative designs, the first criteria we looked at was desirability. To collect this data, we sent a form to participants, and they would have to score the designs on a scale of 1 to 5. The first design got a score of 4.42, the second got a score of 4.00, and the last got a score of 3.92. For our second point of criteria, we had to test the effectiveness. And to do this, we looked at the ultrasonic sensors and saw how far they could read out, and then took the standard deviation. So for design 1, it had a higher standard deviation at 0.63, which when compared to the other 2 was the highest, but it was still relatively low and had low variability. For the second one, because it was made in Minecraft, we couldn't test the variability of it. We couldn't get an accurate standard deviation because it had a 100% success rate. So we just took both data points and extrapolated them and applied it to our second design because it encompassed the same sensors. And then for design 3, it had the lowest variability at about 0.2, and so it was the lowest, and because of that, it was the most consistent and reliable. So the third criteria we looked at was the economic viability, and to do this, we added up each component in terms of price of each design. And so design 1 had the highest total cost at about $137,000 and was not economically viable. The second design had a cost at around $3,000 and also was somewhat economically viable, was the middle there. And then the last one, design 3, had an economic viability rating of the highest because it had a total cost of about $1,000. So the last criteria we looked at was technical feasibility, and this encompassed things like maintenance time. And so to get this data, we couldn't actually test for maintenance time because we hadn't made them in the real world. So we had to take outside sources and apply them to our designs. So for the first design, we looked at car mirrors, which had a maintenance time of about 0.5 times per year. The second design, we used traffic lights, and that also had 0.5 times per year. And then the third design had a radar camera, and that was 1 time per year. So a little bit higher in maintenance, whereas the other 2 were quite lower.
After carefully reviewing all 3 of our design options, the team decided to go with the Obstructed View Assist System, optimizing it into its final iteration shown here.
Our final design, the Obstructed View Assist System, utilizes an array of ultrasonic sensors, speakers, and LED lights to alert pedestrians and bikers of a nearby biker's presence on a bike lane. After optimizing our design, we once again sent out a survey to Purdue students to measure the desirability score of the final design and see how well it would fit the new Purdue aesthetic. After we received the data back, we noticed that we had a new average desirability rating of 4.31, an increase from the previous 3.9. For effectiveness, we once again looked at the standard deviation of the ultrasonic sensor, which stayed the same as our previous iteration, which meant low variability and high reliability. Our maintenance period stayed the same as once per year, as we're using the same reference. For our economic viability, after optimizing our design to be more effective, our total cost to implement the solution is around $3,000, which is still very economically viable. Although this design is very effective in increasing the overall safety of the campus, there are some trade-offs to it. One of these trade-offs includes decreasing the economic viability in order to increase the effectiveness and desirability of our final design. It also has some limitations, including weather that could interfere with the ultrasonic sensors, creating false negatives. On behalf of Team H210,
Thank you for watching our video.
and we hope you choose to implement our design.